I want to start today's lecture with a discussion of a funky property of the F-statistic, the fact that the lowest value is 1. Now, let me just go over why this is, where it may be confusing, where it's coming from. So we know that the F-statistic for a between subjects one-way ANOVA is the between variance divided by the within variance. Now that's systematic variance divided by unsystematic variance. And you would assume, like, well, if I had no systematic variance, I'd have a 0 in the numerator and my F statistic would be 0. However, what's really going on is you still have between over within. However, error is everywhere. You can't escape it. You can try to protect yourself, but it will find you and get in your data. There's nothing you can do. It's like dust. Okay? So between over within is really saying systematic plus unsystematic divided by a pure estimate of systematic variation. That's because, like dust, error is everywhere. So even in that estimate of pure treatment effects that we showed, even that, like, when we change mean replace the numbers, those means are measured with error. So it really is systematic plus unsystematic divided by unsystematic. So if we have no systematic variation, it's 0 plus unsystematic divided by systematic, which resolves to unsystematic divided by unsystematic. If you can view that like an algebra variable, right? Like x divided by x is 1, right? We know that. 5 divided by, if we give them numbers, right? Oh, we're like unsystematic variance equals 5. 5 divided by 5 is 1. 2 divided by 2 is 1. 1,000, lots of variance. Lots of error. 1,000 divided by 1,000 is 1. So that's why the lowest F statistic that you can get is 1, theoretically. Now you will find F statistics less than 1 in your research, and that's because your estimate of unsystematic variation is biased with other forms of unsystematic variation. Don't think about that too hard. There's just error everywhere, even in your estimate of error. Now, what we have been doing with parsing the variance is we've basically been doing a one-way ANOVA. We just haven't done all the steps. So a one-way ANOVA is just an ANOVA that you run when you have one independent variable and 3 or more conditions, and you have one dependent variable. There are 2 flavors: the between subjects, where you have different people in different conditions, and the within subjects one-way ANOVA, when you either have same people in all the conditions, like my example from the parsing lecture, or we have like triplets in the conditions, like they're siblings or triplets, or we have matched people in the conditions. They're pre-matched on some variable, maybe anxiety, maybe height, who knows, could be anything, doesn't really matter. But we use the one-way ANOVA when we have one independent variable with 3 or more conditions and one dependent variable. Now the ANOVA is a multiple step process. So you run the ANOVA, and if your p-value is less than 0.05 or you have a medium effect size, you move up to follow-up tests, which there are 2 different choices that we're going to make: pre-planned t-test or post-hoc tests. I'll talk about those later. If our p-value is greater than 0.05, we're done. We don't need to do follow-up tests. So keep that in mind. Now, I think the best way to just learn how to do an ANOVA is to do one. So we have a very simple experimental design with very simple data that I made up. This design, you have participants, different people in each of the conditions, looking at happy, sad, and neutral emotional faces. And we're just measuring how long they look at the face. How long do they choose to look at the face? So this is a very simple experiment. Let's see if people spend different amounts of time looking at different faces and how we would go about breaking down this ANOVA. Now it's between subjects, so it's a one-way between subjects ANOVA. All right, so here's how we entered the data for this problem. We have 3 conditions, right? 1, 2, and 3. 3 observations in each condition. Time spent looking at the faces. When I set up my data, I did in fact add value labels there. So if we go view value labels, which is smart because then you always get labels for your conditions. You really should add your view value labels to this problem. Make sure you're doing that. And if you forget how to do that, you click inside your coding variable for your independent variable, you click these three dots, and like if I wanted to add another level, let's say for angry, maybe. Let's say I had a different experiment. I'm going to remove that since I didn't have that, but it's super simple. But now that we got that all done, how do we run a one-way ANOVA? It's a great question, right? So analyze, compare means, one-way ANOVA. Now this is one way between. It only works for one way between. I'm going to pull my variables out of here. So this is my dependent variable, or time spent looking, and my independent variable is the factor, which is my emotion face. Now we have different options. We're going to use these later. Contrasts, I'll talk about later, but I want to show you all the options. So I'm clicked on contrast. Post hoc tests, I'm going to click off of those options. Other options that I have, one of the things that I will change for my one-way ANOVA is my confidence intervals to 90%, because 90% confidence intervals work better with the F distribution. I'll explain that in not too long from now. You can click descriptive statistics if you want. That might help you out, but I'm going to show you a way to get those descriptives eventually. And bootstrapping is something you'll never have to worry about, but that's okay. All you do is then click OK, and you're going to get a very... I'm just going to do it again so it goes on one page. Analyze. This will be good for you. Compare means, one-way ANOVA. I didn't really have anything except for my options. I changed it to 90% confidence intervals. I'll explain why. Not too far in the future. I click OK. And what you see here is that you get your ANOVA table, which is very pretty, right? Look at this. This is probably the only thing SPSS gets better than anything else, is this ANOVA table. Between groups, within groups, total, these are your components, sum squares, degrees of freedom. This is variance, they call it mean square, your F-statistic and your p-value. You have your point estimate of your eta squared, your 90% confidence interval of eta squared, but we have everything we need. And we did it in 3 minutes. So we are trying to disprove a null hypothesis here as well. The null hypothesis for a one-way ANOVA is that there's no difference among your 3 or more means. And essentially, we can represent that as, the true population mean for time spent looking for happy is equal to the true population mean for time spent looking for sad, which is equal to the true population mean for time spent looking for neutral. Now, in general, we'll say F equals 1, and that's really the only way. An F statistic is the only way to tell if 3 means are different from each other. There's no other statistic we have that even gets close to looking at like the difference between 3 means. At least it's not a statistic I've ever been taught. So ultimately, though, this hypothesis shows up in this generic F graph down here, this F distribution down here, where you can see like the peak is basically straddling 1, and that's the most common F statistic if the null were true. I'm going to complicate that a little bit. So the null hypothesis for F statistic is generally that the F is equal to 1. But there are different F distributions based on your degrees of freedom. So we have 2 and 6 degrees of freedom, and the actual F distribution that represents our null hypothesis being true is presented in the upper left-hand corner. So that's actually the null hypothesis we're trying to disprove. Now I do want to show you, if we just had degrees of freedom 3 and 6, that's the upper right-hand corner, and that shows the null hypothesis F distribution for that specific data set. When you have 4 groups, you get this nice hump. When you have
even more observations, you get that traditional null hypothesis F distribution that you see right there in the bottom left-hand corner. But ultimately, I want you to know that there are different F distributions for different combinations of degrees of freedom in the numerator and degrees of freedom in the denominator. So for this case, between, over, within, right? So the degrees of freedom between, degrees of freedom within. That's how we present the statistics.
So here is our ANOVA output. And what I really love about it is it shows us everything we need to know. Between, within, total. It shows us those different components. And the sum squares divided by degrees of freedom is variance. They call it mean squares, so be careful there. But they don't calculate the total variance. That's fine. You don't have to. It's not really part of the calculation. It's just there. Our F statistic is our variance between divided by our variance within. And our p-value for this is 0.001. So the probability of sampling an F statistic as extreme as 27, given this null hypothesis that I just showed you, is less than 0.001 probability, or less than a 0.1% chance of that happening. So what this is telling us is that there is a significant difference somewhere among our three means, and we're going to have to find it. So in my graph making program, when I graph this, it doesn't even, you can't even really see it. That's how small the p-value is. The p-value is so tiny it barely shows up on the graph, but that's our F statistic. The p-value is the area under that line, which is less than 0.001. But yeah, we've clearly disproven that null hypothesis that our F statistic is equal to 1.
All right, so now I've talked about eta squared, I've talked about partial eta squared. This is our preferred effect size for an ANOVA. Now, ultimately, I was telling you it's the percentage of variation that you cause. That is true, that's how we interpret it. Now we have some limits for a small, medium, and large effect according to Cohen again. So a small eta or partial eta squared is 0.01, a medium eta squared is 0.06, and a large eta squared is 0.14. So we got to remember this now. I wish it was the same as Cohen's d, but it's not. So we're going to have to remember 0.1, 0.06, 0.14. Okay? So these are our effect sizes for eta squared. Let's go look at our effect sizes from our SPSS output.
All right, so here we get a very beautiful output for our eta squared and our 90% confidence interval for our eta squared. Why did I choose 90% confidence interval here? Well, in the statistical literature, it's been suggested that the 95% confidence interval is too conservative for eta squared, so we should use 90. I can find a citation if you want, but it's Daniel Lackins' work. Outside of that, I have to say I'm really excited about SPSS's use of effect sizes in this edition, but they only include this 90% confidence interval for eta squared, just for the between subjects one way ANOVA. None of the other ANOVAs will use. So I'm not going to have two different interpretation metrics for you. So essentially what I'm going to say is, like, you can look at this and you know what it means. Right here, we know that the effect is large to large based on our criteria. 0.14 is large for an eta squared. But really, the omnibus ANOVA is, should I do follow-up tests? Okay, P's less than 0.05, yes. Or your effect size, your point estimate of your eta squared is at least medium, which is 0.06. So in this case, what does our eta squared tell us? Multiply it by 100. Right? 90% of the variation in our data set is driven by our manipulation. So this is a very good, controlled, highly effective, highly scientific study, right? Like, oh, 90% of the total variation in this data set was caused by my experiment? That's a lot. In fact, because I made up the data, of course it's a lot, but ultimately 0.16, 16% is considered a lot in behavioral sciences. I wasn't part of that conversation. It seems a little small to me, given the common sense interpretation of percentage.
but they're basing it on their estimation of average effect sizes in our field. So 0.06 is average, 0.14 is large, 0.01 is small. So essentially, that's how we're going to use it. This suggests 90% of the variation was caused by us. That's why it makes sense, right? It's a very sensible metric that is greater than 0.06 by a lot, right? Like that 0.06, that 6% value. We have a very large effect size. Even if we had a non-significant p-value, I would suggest go on and do your follow-up tests. Now, instead of writing out a result here, I think it's easiest just to use an ANOVA source table. You can see this looks very similar to what SPSS gave us. And eventually I'll migrate this to a APA style one for you to use in your final papers. But right now, I just want you to make a table that at the top has predictors, sum squares, degrees of freedom, variance, F-statistic, eta squared, and your p-value. So if you notice, on my predictors, I call it my face manipulation. I don't call it between because, I did create that manipulation. That's what it represents. Instead of within, I called it my error term. That's just general practice in the field, and total is still total. Sum squares, degrees of freedom directly taken from SPSS. The variance is called mean squared in SPSS, directly taken from SPSS. Analysis of variance, F-statistic, your between over within, which is your manipulation over your error. Eta squared, 90%, p-value 0.001. You just have to do this table for your results. So ANOVA is kind of like a stepwise process. We found a significant omnibus test. That's what we call it. That F statistic was significant. That means there's a difference among our three means. We don't know where the difference is, so we have to do follow-up tests to find it. Now, there are two options in follow-up tests, and I'm going to teach you about them both. The first option is you just run all possible follow-up tests. This is called a post hoc approach. This is the most common approach taken for research methods students. It's pretty easy to accomplish. The other approach is planned contrast, which you run only tests that examine your specific hypothesis. It's an advanced topic that I want to cover. I'm going to cover in the next slide, but it's not one that you have to pay attention to, so you can fast forward if you'd like. Now, planned contrast, they exist before you ever run your ANOVA. They're your hypotheses. They're planned comparisons that you want to make. They can be simple mean comparisons, and then you just run a simple t-test. So that's one form of a planned comparison. However, we often have these complicated hypotheses. So a planned comparison is just a weird weighted t-test. So in this example, let's say I had a prediction that people that would spend less time looking at happy faces than they did sad or neutral faces, where they would spend an equal amount of time looking at sad and neutral faces. Well, I need to create coefficients, contrast coefficients, to test this idea. And those contrast coefficients would be assigned, -1 would be assigned to happy, 0.5 would be assigned to sad, and 0.5 would be assigned to neutral. Now, SPSS uses these codes to say, I'm going to run a t-test. I'm going to compare happy versus the average of sad and neutral. Or we could run something like a linear contrast where we're predicting that scores will increase linearly across the conditions, where happy is the least, sad is the middle, and neutral is the most. Well, that contrast is -1, 0, and +1. This is also a special case. This is a two-group comparison contrast, so really it's also just a t-test between happy and neutral. If we had more groups, the linear contrast wouldn't do that, wouldn't drop a group out in the middle, but it does here. But that's okay. You could also have a curvilinear relationship, like the Yerke-Dodson's curve, right? Where you're predicting, in this first example, well, people will spend less time looking at happy, more time looking at sad, and less time looking at neutral. Or you can make the reverse prediction. People spend more time looking at happy, less time looking at sad, and more time looking at neutral. But both of these are just t-tests that are putting happy and sad together, or happy and neutral together, and comparing that to sad. So I just want to review these follow-up tests. You're going to be expected to run the post-hoc test. That's what all research methods students do. However, this is not necessarily the best method. What you should be doing in real science is making predictions and testing those predictions directly. I showed you the contrast method. Those contrast numbers go into SPSS, and then SPSS does these weighted t-tests that combines various means together and compares them to other various means. So ultimately, that's all that's going on. But now let's run our post hocs and our planned contrast in SPSS. So we have to get our post hoc analysis. How do we do that? Right? So you're going to click Analyze. Sorry about that. Let me make this big. Analyze, compare means, One Way ANOVA. You're going to rerun your One Way ANOVA. I'm going to change some things though. Remember I changed my confidence interval in the options from 95 to 90 earlier. I'm going to change it back. I want to also point out, if you want your means and standard deviations in your ANOVA output, you click this descriptives button. So I'm going to go ahead and click that for you because you're going to need those. Yeah, you really won't, but you might want them. For your post hoc options, you're going to choose Fisher's LSD. I'll tell you why later. Okay, but you're going to click LSD on this option. And then we're going to click OK. And what you notice here, oh, these are all your descriptive statistics. Look, it gives you some nice descriptive values. Your means and standard deviations are what's important there. If you notice with this data set, standard deviation is 1 because of how I set it up. Now also, what do we have here? We still have our ANOVA tables, so we have that again. We already had that, we already interpreted that, but this is the only way to get post hocs. You didn't know if you needed to run these beforehand. You can always run these beforehand if you want. You can just run everything if you'd like. We got our ANOVA effect sizes, and we have our post hoc tests. And like I said, post hoc tests are basically just all the t-tests. So essentially what we have here is like a t-test comparing happy and sad, happy and neutral, sad to happy, sad to neutral. This is the one that's in the subtraction first. So this is happy minus sad, -3, because people spent less time looking at the happy faces and the sad faces. Happy minus neutral, -6, same reasoning. Happy less than neutral. Sad minus happy, that's positive because people spent more time on sad than happy. Neutral minus happy is also positive because people spent more time on neutral than happy. Now, you can see that 3 of these tests are identical. Like happy and sad is the same as sad and happy. It's just the numbers are flipped. You can basically see that, right? Those numbers are just flipped. Oh, like this is a -1.02. This is a positive 1.002. -4.997, positive 4.997. -3, positive 3, so forth. Now, SPSS almost got it right. They give you a 95% confidence interval of the mean difference. They gives you p-values, right? But it doesn't give you the 95% confidence interval of Cohen's d. I want to say one more thing about these specific analyses. Now, they are basically t-tests, but they take care of a problem that I'm going to talk about later. So they're not exactly t-tests. But ultimately, you see, like, I don't have my 95% confidence interval of the Cohen's d. Well, you can get that through the independent samples t-test. So let's go ahead and do those. Analyze, compare means, independent samples t-test, right? We're going to define our groups. We're going to have to do this 3 times. So I didn't really make a prediction here, and I know that I just am going to, for this example, use the mean differences that are positive. So I'm just going to act like I predicted that the sad would be looked at more than the happy, and that the neutral would be looked at more than the sad. So sad and happy, sad's looked at more than neutral, so larger number goes first. Gonna click continue, gonna click OK, and you can see it gives me my 95% confidence interval of the Cohen's d. I also get, again, the means and standard deviations, but I don't need that now that I have descriptives. I don't need this. This t-test is worthless. You can delete these if you wanted to. you just click on it and hit the delete button, right? You can see that. If that makes you happy, you can do that. But ultimately, I'm going to do 2 more of these. Analyze, general, compare means, independent samples t-test. I'm going to define my groups. 3 minus 1 predicting neutrals greater than 1 as well. I can go ahead and delete and delete. I don't need that data. Analyze, compare means. You don't have to delete, but it just sometimes makes life easier. Independent samples t-test, and now I got 3 versus 2. Neutral versus sad. Clicking continue, clicking OK. Delete, delete. And why did I run these? Why did I run these 3 different t-tests? Because I need these 95% confidence intervals of Cohen's d. I need these Cohen's d's and these 95% confidence intervals. So essentially, yeah, that's why I ran these tests. And now I have everything I need from SPSS to do the post hoc test. Okay, now I'm going to switch to the contrast. I just talked about contrast. You can skip this part, move on to when the PowerPoint starts again. But how would I do a contrast? So analyze, compare means, one way ANOVA. And I'm going to go ahead and click off my post hocs because I don't need them. So I'm just going to hit continue there. But I click in this contrast box. And that one contrast, I predicted that SAD would be less than the combination of I predicted that happy would be looked at less than the combination of neutral and SAD, which would be looked at the same way. So I'm making one of those weird t-tests. So when I added my 1, 2, and 3, my definition of my groups, 1 is happy, 2 is sad, 3 is neutral. So my first coefficient I'm going to add is, well, I'm -1 because I'm predicting happy is less than the other 2 groups, 0.5 and 0.5. So that's one contrast I want to look at. I could look at other ones. I could add contrast there, right? In fact, I'm going to go ahead and add one. I'm going to click next. I'm going to add another contrast, which was my -1 for happy, 0, and 1. This was my linear contrast that I just want to show you how you would do a linear contrast by hand if you wanted to. Also, you can do a linear contrast by clicking this box and clicking linear. So now I hit continue and I hit OK. And you can see I have my contrast, my predicted contrast effects. It shows you them up here, which is kind of nice. Ultimately, my contrast test shows up here. So this is testing my direct contrast. Well, first, let's just go back. So this is all the output. I have descriptives clicked still, have my ANOVA. When I click the linear contrast, this is the test of the linear contrast right here. Okay, so this does follow a linear relationship. So my post-hoc test suggests a linear relationship. So, well, not my post-hoc, my follow-up test suggests a linear relationship. So the linear contrast is significant here. Now I tested 2 contrasts. One was is happy different than the combination of sad and neutral. And so that contrast 1, is significant. Contrast 2 is my linear contrast, which is also significant. Now, the one thing I wanted to show you is I just ran the linear contrast twice, okay? Ooh, and it also gives me contrast effect sizes. Look at this nice estimate here. I get the Cohen's d, and I get the 95% confidence interval of the Cohen's d for the contrast effects, which it doesn't give me for the post-hoc test, but that's okay. So contrast effects are kind of nifty. If you wanted to, you could make all the contrasts that you want to make for all the different comparisons and get your Cohen's d. So that'd be another way to get Cohen's d. But ultimately, when you're looking at this, I want to show you, I got two linear contrasts. That linear contrast was contrast 2. Its t-value is 7.348. Its p-value is 0.001. My linear contrast, which is tested directly right here, the one that you click on in SPSS and test the linear contrast directly, has an F of 54 and a p-value of 0.000. So the p-values look identical. Now, I don't think I mentioned this earlier, but T and F are related. T squared is F. So if you take 7.348, or even click in there, if you take 7.348469 and square that, you will get 54. So T squared is F. I want to show you that when you do it with SPSS, like if you put the contrast in manually, or if you let SPSS's polynomial contrast do it for you, you're getting the same result. So I just wanted to show you those are the same thing. But ultimately, with the contrast, you can test whatever you want. And if you have estimates of effect size clicked, you're going to get this nice 95% confidence interval of your Cohen's d for each contrast, which I think is just amazing, right? Like, that's pretty cool. Each of my contrasts have a Cohen's d, and each of my contrasts have a 95% confidence interval of the Cohen's d. So ultimately, you didn't need to learn this part. That was for fun there. I'm not going to really tell you how to write these up. Essentially, if you'll learn from the other analysis. But that's how you get your postdocs. So with post-hoc tests, you run into the problem of multiple comparisons. Now imagine you ran 100 tests in a null population. 5 of them will be significant just by chance. And that's based on like our p-value cutoff. We call it alpha, right? So you can't just run all the tests and be a good scientist. You will find significance in quotation marks, but what you're really doing is ruining our field. Now let's say you found a p-value of 0.05 for 1 of 3 tests. What is the real p-value when you run 3 unplanned tests like this for, your p-value is 0.05? Bonferroni would say, well, you ran 3 tests. So really your p-value is 0.05 times 3, or 0.15. Tukey's like, hey, you ran 3 tests. You didn't plan to run these tests. And so really your p-value is greater than 0.05. Fisher, with the least significant difference, the Fisher's LSD, is like it's greater than 0.05, but not as far out as Tukey suggests. We use Fisher's LSD because in our studies, we're underpowered. Y'all don't have enough participants to find good effects. So what you need to do is, when you're following up a significant ANOVA, is you need to run a Fisher's LSD. But ultimately, the problem of multiple comparisons means that the more tests you run, the more likely you are to find significance when significance doesn't actually exist. And that's a problem for science. So here's our Fisher's LSD result. What do we see? Well, we got happy versus sad, happy minus sad, mean difference of -3, p-value is 0.001. Got a 95% confidence interval, the mean difference. Those are hard to interpret, right? So we got that comparison. We actually have it twice, sad minus happy, 3.8, 0.01, right? So that's the same exact test. If you notice, look at how the numbers, how the lower and upper limits are flipped and the negative signs are removed, right? That's the only difference there. But we can see happy versus sad is a significant difference. We can see happy versus neutral is a significant difference. We don't know the effect size yet. We want to see that. We can see sad versus neutral is also a significant difference, or neutral versus sad. So you can look at these all those different ways. But yeah, so this is what this output means. It's just these 3 t-tests run both ways you can run them. So here's all our data for our post-hoc analyses. We have all of those individual Fisher's LSD results up in the upper right-hand corner. Well, we also need our Cohen's D's and 95% confidence intervals for the Cohen's D's. Well, right here, it's like, oh, I kind of deleted some stuff when I was making that video. You saw me do that. And it's like, oh, what Cohen's d does this refer to? If you look up there, it's emotion phase 2 versus 1. So this is sad and happy. And so my Cohen's d is 95% confidence interval 0.38 to 5.5. This one right here, if you look up here, test group equals emotion phase 3-1, neutral and happy. Effect size, Cohen's d is 6. 95% confidence interval 1.7 to 10.27. And over here we have another Cohen's d, and this is going to be for 3 to 2, so that's neutral to sad. And what do we have here? We have a Cohen's d of 3. We have a 95% confidence interval of 0.38 to 5.503. I do, because I made the data linear, you're like, oh, we have two exact results that are two totally different comparisons. That's just happening because of how I set up the data. That is not a standard of how data will come out. You won't have two comparisons that are the same. That's just because when I set up the data 1, 2, 3, 4, 5, 6, 7, 8, 9, right? The difference between group 1 and 2 is the same as the difference between group 2 and 3. So no big deal here. But now you have all the data to complete your post hoc table that I'm going to show you next. But this is all the data you have here. Ultimately, what can we see? When we look at all this, we can see that overall, all the means are significantly different. But the strongest difference, the most reliable difference, the best scientific difference that we're finding is the difference for happy versus neutral faces. Now, how do I want you to interpret your post hoc test? We've got a chart for our normal ANOVA. I want a chart for our post hoc test as well, just because it makes it easier. So you have group happy, sad, neutral are represented there. You have the ends, the means, the standard deviations. I can get those means and standard deviations from my output in two places, the descriptives, or from the independent samples t-test. So I have all my means and standard deviations in there. That's important for me. I want those in there. That's good scientific practice to include that data in there. And then I got my Fisher's LSD comparisons. I got my P's and my D's, and my 95% confidence interval of my Cohen's D's. P's and my D's, 95% confidence interval of my Cohen's D's. P's and my D's, 95% confidence interval of my Cohen's D. So here's the three things that I keep focusing on. It's a significant difference. I just want you to write significant or non-significant. Was it great science, okay science, based on the interval, right? The width of the interval. So happy and sad, that's okay science. It's like a medium to large effect. So that's okay science. And then I want you to put in parentheses your worst case scenario. Medium-ish. Worst case scenario, this is a medium-ish effect. Maybe you could write a little less than medium, but basically medium. However you want to interpret 0.38, I'm fine with, right? We know what the rules are. 0.2 is small, 0.5 is medium, 0.8 is large. Well, when you're basically 0.4, what are you going to say? I'm going to say medium-ish. You might say like a little less than medium, small to medium. I don't care, as long as it makes sense, okay? And then we do the same thing for all the other comparisons. So you just have to write significant or non-significant. They were all significant. Was it okay science or great science based on the width of the interval? And then tell me that worst case scenario. Worst case scenario, this is a medium effect. Worst case scenario, this is a large effect. Worst case scenario, this is a medium-ish effect. But that's all you have to do. Make this chart, and that's all I want to see. All right, so this is the same data we had before. I had to alter the ordering of it because otherwise we would have all the error would be due to subjects or participants. So you can see I still have 1, 2, and 3 in the happy face condition, 4, 5, and 6 in the sad face condition, and 7, 8, and 9 in the neutral emotion phase. In the between subjects design, remember we had like 9 participants, so they had 9 different data points. We didn't know where they came from. So this is the same data. I just had to alter it around a little bit so that it wouldn't cause SPSS to not run and not find p-values. Because like if it was 1, so if you can imagine this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Like all the variation within subjects variation is explained by the different participants. So we had to get rid of that, and this is what we chose to get rid of that. I just showed you this data. And how do we enter it in SPSS when it's a within subjects design? Well, within subjects design is one row per participant, or one row per matched group, or one row per siblings, right? Like all those dependent samples, one row per the dependent sample, right? Well, in this case, Frodo is their own, participated in all three conditions. Sam participated in all three conditions. Pippin participated in all three conditions. So essentially, this is how you set up your data, right? Oh, okay, per participant, one row per participant. That's how you always set up your data in SPSS. You just gotta be careful if you have like twins, which you're not gonna have a twin study, or you have matched pairs. Maybe you're gonna have matched pairs, but I doubt it. But this is how you set the data up. Now, how do we analyze the data and find our one-way ANOVA? Analyze, and you're like, oh, I'm gonna go to compare means. This is where compare means stops working for you. You need to go to general linear model and click repeated measures, because this is a repeated measures design, right? That's one of my favorite definitions for it. So now we have dependent samples, paired samples, matched pairs, and repeated measures, right? Those are all the same name for the same idea, same design. So I did this earlier, as you can see, but let me just remove this. So I'm just going to call my within subjects factor, I'm give it a name, emotion face, number levels 3. Now I click define. And then I'm like, okay, I got to click in my 3 emotional faces. I have no covariates between subjects factors. This is all I have. And then you click on postdocs, you're like, wait, I can't do any postdocs. That's because the postdocs are just for between subjects designs in SPSS. But if you click in the EM means and click, go ahead, click your emotion face in here, click compare your main effects and click LSD and click continue, you're now going to get your postdoc tests, saves. In your options, make sure your descriptive statistics are clicked, estimates of effect sizes are clicked, click continue, click OK, and now you get all this output and you're like, okay, what does it mean? First, you got a key code, 1, 2, and 3, 1, 2, and 3. Happy, sad, neutral. Then you have your descriptive statistics, means and standard deviations, great. Multivariate test, you don't need. You can delete it if you want. Test of sphericity, you don't need. You can delete that. Test of your within subjects effects. So this right here is giving you part of your ANOVA. Particularly, it's giving you your between subjects component and your error component, your actual error component, which is, your within minus subjects. So this is error. Okay. We have our sum squares. We have our degrees of freedom. We have our variance. We have our F. We have our p-value. We have our partial eta squared. And you're like, okay, so what about all these other values? These do not matter. Just ignore those. Okay, those do not matter. Okay, same thing here. Ignore these. They do not matter. Just that first line. That's what we're going to deal with right now. Okay, so SPSS is giving you a lot of output here. Test of within subjects contrast. If you want to play around with contrast, it's already giving you the linear comparison. So we can see that the linear comparison is significant. Oh, it's also giving you the quadratic comparison, and the quadratic comparison is not significant. Now that's like the curvilinear aspect. So, but ultimately that's useless to us. I'm just connecting it back to what I talked about earlier. So anything you mess around with the contrast in will show up in there, but ultimately delete that. Now, test of between subjects effects, you're like, wait, didn't we just do that? Yeah, it's a poorly named component. What you see here is that the error is 0.667. So that's a sum squares error. If you notice, our sum squares error for the emotional face is 5.333. If we go all the way back up here, it used to be, sum squares used to be 6 for the within group, right? So now, if we're looking at this, so this plus plus this. 5.333 plus 0.667 equals 6. This is our subjects component. Okay? So that's important. Degrees of freedom subjects, 3 minus 1. Variance subjects is right there as well. And it's testing an intercept. Don't worry about that. This really doesn't matter. That doesn't matter to you, but this does. So you're good there. So that's pretty nice. But this is our subjects component. And then we get these estimates, these means and standard errors. We don't need the estimate component there. So I'm just going to delete that. We have our pairwise comparisons. These are the Tukey's LSD. And I'm going to blow your mind in a second, though, because you're going to see something that's pretty interesting. These multivariate tests you don't need. So I just delete stuff we don't need. But ultimately, you don't have to delete stuff. You can keep it. But ultimately, that's kind of like my way of dealing with it. But that's everything that we had before. Now, what don't we have? We don't have the Cohen's d, or the 95% confidence interval of Cohen's d. So let's go ahead and do that. Analyze, compare means, paired samples t-test. I've already done it, but you can see, like when I entered them in, I just said, look, I predicted that people would spend more time looking at neutral than they would sad faces, and more time looking at sad faces than they did happy faces. That's what the data show. So I was just making that prediction to make my life easier. But when you're entering in the means, the first one you enter in should be the mean you are predicting to have the group that you're predicting to have the largest mean, smaller mean, larger mean, smaller mean, larger mean, smaller mean. Sad's greater than happy, neutral's greater than happy, neutral's greater than sad. Okay? Make sure my estimates of effect sizes are clicked, my standard deviation of the difference is clicked, and we click OK. And so right down here, we get our point estimates of Cohen's d for every single comparison. We get our confidence intervals range for every single comparison that I ran. And what we can see here, let's actually look at the data. I want to look at the post hoc data real quick. I want to show you something. So we found this omnibus F test. After we removed the effect of subjects, right, we found only one significant difference. That difference is between happy and neutral. Neutral and happy, significant. Happy and neutral, significant. These are the same test. Okay? And I want you to look at that. Like you got 0.095, 0.009, 0.122. When we ran the t-test, 0.095, 0.009, 0.122, you're getting the same results that you are getting when you run the LSD test for a one-way ANOVA. You're getting the same results. So you don't have to run those estimated means and that LSD test, because it's not doing anything different than just running the paired samples t-test alone. Now remember, I said the LSD tests are the least conservative tests. Those are the ones we run for our projects. And the least conservative test of all is just running the 3 t-tests. So essentially, I think it's important to know that for a within subjects one-way ANOVA, the LSD is the same thing as running all the t-tests. That's all it is. But ultimately, that's what we found here. That's what we're finding. These are the results here. But let's just go over it one more time. What's where, right? Between subjects is called a motion face. Error, that's within minus subjects is called error. We don't have within given to us, and that's okay. We don't need it. Down here in the test of between subjects effects, this is our sum squares due to subjects. It's labeled error as well. So keep that in mind. You're going to want to pull that out. We have our Tukey's LSDs, which are nothing more than our paired samples t-tests. So I've shown you that as well. And ultimately, we also have our effect sizes for each of these comparisons. And this is all our data. So what do we do with our data once we have it? Let me show you. I'm not going to show you exactly for this data because your homework is to report this data. All right, so you have to fill out your ANOVA source table. You're going to have your face manipulation, your error term, which is within minus subjects, your subjects term, and your total term. I'm not going to make you put within in here because within is error plus subjects. That'll just make it too clunky. But let me show you where all this information is coming from, right? Well, the emotion face, that's your face manipulation, right? So you got most of that whole first line's completed for you. Then you got your error term, which is this error term right here. You got that completed for you. Your subjects, that's this error term right here. You just have to fill out the first two. That's completed for you. Total is going to be the sum of all the rest of this. So total sum squares is the sum of between error and subjects. And total degrees of freedom is the sum of everything else. So 4, 5, 6, 7, 8 total degrees of freedom. You can see that. So the information is right here to fill out this table, right? Emotion, error, subject, add for total, and that's all you need to do. So now you want to take your post hoc data and you want to fill out this form, particularly, right? We already know our means and our standard deviations. Our p-values changed, our Cohen's d changed, our 95% confidence interval of Cohen's d changed. So we're going to put that information here. So then just give me a short interpretation of your results. Were the three means different overall, that omnibus ANOVA test? And then how are the three means different? So, you know, essentially you're looking at your data to make some conclusions. Okay? I don't expect more than a couple sentences here. Just short interpretation. So right now you're seeing basically all the data you need to complete this homework assignment. I want you to complete those two charts, make those two tables, and give me that interpretation. I also want you to feel confident you can get these various outputs. So make sure you can get these outputs from SPSS. But for today's homework, you got this second output, right? It's right in front of you. Now complete your homework, which is complete those two charts or tables and give me a short description of what all this means. So your homework is just finish reporting this within subjects One Way ANOVA. I want both tables. You will have some short notes for your post hoc table. Your p-value, was it significant or not? Your C, your confidence interval, quality science, your worst case effect size, what was that? And also just a short interpretation of the results. Well, was there a difference between your means? Yes, there was. Where was the difference? There was only one place that it was different. What you should be able to do at the end of this lecture, I give you extra stuff per lecture, but what you need to be able to do is you need to be able to run One Way ANOVAs and SPSS and report them with these two tables and just a short interpretation.